A year ago, many of you tested the Crescent Bay prototype. We were tasked with taking the Crescent Bay and turning it into the Oculus Rift. Now, virtual reality is driven by software. The reason we're here today is if the device doesn't fit you, the software, the content can't shine. We had to make sure that the Rift fits you, is comfortable, to get the best possible VR experience. Now, why us? Why are we tasked with taking this prototype and bringing it to the masses? My name's Kalinowski. I lead the product design engineering team. I'm going to tell you a story. When I was 5 years old, my parents, after weeks and months of asking, got me a remote control car for Christmas. And the first thing I did that same night is I took the remote control car apart to see how it worked. And they had no idea this was going to happen, and they were pretty frustrated about it because it was a really nice toy. Flash forward to 1989, 4 years later. It took me a full 4 years to get them to buy me another car. This was the Batmobile. It was the hot toy, and they said they'd give it to me, but under one condition. I could not take this thing apart. And so here I am in the basement, checking it out. It's got this cool hatch that slides forward and back, and I'm thinking, I really want to get my Batman figurine into this car. But I know I can't take it apart. So I lasted about 4 days until I broke down, took the hatch off, and just kept going. I couldn't stop. Fast forward to last year, when I first tried the Crescent Bay prototype. I wasn't even part of Oculus at that time. But I'll never forget when that huge dinosaur came right up to me, roared right in my face, and walked over me. It was like I could feel the floor shake. And I knew that I had to be part of the team. It took me back to being that 5-year-old kid, staring at that car, trying to figure out how it worked, and trying to figure out how to make it better. But now I was an engineer, and I could actually put things back together again. I knew if we do this right, we can get the headset to disappear even more in the face of this amazing content, in a way that makes the content come to life even more. It was a dream for me to work on such a disruptive technology. So it was pretty clear I was going to lead the product design engineering team on the Rift.
Hi. Hi, my name's Stephanie Liu, and I lead the hardware engineering program management team here. A bit about me. So growing up, it's not a surprise I took an affinity to the math and sciences. My mom's an accountant and my dad was a mechanical engineer. Though it wasn't until college that my interest in engineering really got sparked. I would walk by the machine shop to and from golf practice every day, and I saw some of my classmates and dorm mates making projects on the equipment in that machine shop. I saw them make magnifying glasses out of blocks of brass and plastic. And at that moment, I knew that I wanted to be an engineer, so I too could make things that I could hold and give to my friends and family, and eventually work in an industry that I could make things and see them out in the world and see people using them. So also I was going to and from golf practice, where my golf coach drilled into me to be early is to be on time is to be late, and to be late is simply unacceptable. So you can imagine the combination of my interest in engineering plus the desire to get things done on time and even early led me to a career in program management. So how did I end up here at Oculus? Why Oculus? I remember the very first time I did the Crescent Bay demo. I was transplanted onto the top of a skyscraper. And I remember looking down, and I'm a daredevil at heart, so my heart rate started to go up immediately. And I actually reached out trying to grab a handrail. And at that instant, I was sold. I was so drawn to this technology that I thought, I want to be a part of this incredible team and this incredible company, and I want to try to find a way to help get VR out to as many people as quickly as possible. So what do the hardware EPMs do here? We get stuff done. We help teams get the product out the door. We corral all these different teams, product design, electrical engineering, optics, software, and we try to get everybody moving in the same direction with the common goal of building the best possible experience and the best possible product. And also, especially on hardware, it's the best possible hardware to best serve the software. We help the engineering teams decide when is it good enough. Because as I'm sure you guys are all familiar with, if engineers left to their own devices, engineers can continue to iterate and iterate and iterate. And sure, you can always make things better, but there has to be a time where you put your pencils down and you can ship the product. We also help identify risks and solve problems by putting the right people to resolve those problems. And often I liken my job to being a professional whack-a-mole player. When problems crop up, we just try to hammer them down as quickly as we can. And many problems we do solve with more finesse than a giant hammer, but I think you get the point. So as part of the EPM team, we had to work really closely with the engineering team to figure out what's the best possible process for product development here. VR is a totally new technology, and new technologies deserve a new custom process. So in consumer electronics, in an industry which I've worked for many, many years, development process tends to be very serial, like this diagram here. The designers come up with an idea, they pass it on to the engineering team. The engineering team figures out how to take this design, it's a concept, and quantify it and to build it and turn it into something real. And then they pass it off into the operations team, which figures out how to take these prototypes and scale to millions. But that process wouldn't work here at Oculus because VR is so interdependent. Everything touches everything else. And we can't just work on design, then engineering, then operations. So we have to do all of these things simultaneously and in parallel. We can't optimize around any single team or any single feature. We have to optimize for the entire experience. So often I liken developing hardware to building a house. You might start with a concept, then you have an architect or a team of architects figure out how big each room is, how tall the ceilings are. You have specialists that come in like plumbers and electricians to help you get the whole house to be what you want it to be. So take an example. Say you're building a house and you have an 80-inch TV that you're really trying to get into your game room. But this TV is a little bit too big for the blueprints that you have currently for your house. In most companies, we would just take that 80-inch TV and cram it into this room and it would look awkward. But we don't do that here at Oculus. We make sure that each team is optimizing around that whole experience. So as an example, we might look at the optics team, which would find a way to thin the borders around the TV, but keeping that same 80-inch viewable space. And then we would work with product designers to figure out how do we make this room bigger, and what other rooms can we take some space away from so that we get this full experience. So again, each of these dots on that right-hand side represent teams within Oculus, and we all have to work together and in parallel to create the best possible VR experience.
Thanks. So what is a product design engineer? That's what I do. We take the vision of the product from the industrial design team led by Peter Bristol, who's here somewhere, I think. The industrial designers imbue the product with its soul. That's how I think about it. The look and the feel, the way the customer interacts with the product, that's something that we really work with them closely on to achieve that dream. You could think of product design engineers as taking the qualitative and making it quantitative. Every single part you see behind me is a custom part designed from the outside in to achieve the look and feel from industrial design, but also to make sure that it achieves all the technical goals from every other team. We take the feeling and make it real. And this is a ton of parts. Each of these parts is custom, down to every single screw. So somebody on my team, there's about 20 of us, has gone into every single one of these parts, designed it in 3D, computer-aided design, figured out all the tiniest dimensions and how all these parts are going to go together, and also determine the material we're going to make it out of and how we're going to manufacture it. It takes a ton of talented engineers to make hardware, and we're just one of those dots on Stephanie's last slide. We're really, really lucky to be part of this incredibly talented team. A note about hardware. Unlike software or potentially content, we ship this thing once. We can never update it. It's in your hands, that's it. So you've got to work really hard to make this the best possible product we can. In this talk, we're going to go through 4 examples to describe what we learned in VR. But all those learnings actually boil down to one concept. The summary is this: you can't get the look and the feel, the industrial design of the product right without getting awesome, great prototypes. But you can't get awesome, great prototypes unless you get the ergonomics and fit right. It's not like other products. You've got to get it all right at the same time. This is what makes VR so very hard to develop hardware for. I'm a big motorcyclist, and I love going out motorcycling on the weekends. My favorite thing about biking is that you're out there, and suddenly everything else disappears, and you're just there with the road and your bike. That doesn't happen. That flow, you don't achieve that flow if your helmet's too tight, or you're worried about your gloves, or you're too hot in your jacket. So everything that touches you has to be right. That comfort has to be there for you to get to that flow state, for you to be immersed in your ride. And the same exact thing is actually true for VR. It's the same exact thing. Comfort is key. Comfort gets you immersion. Immersion gets you presence, which we've talked a lot about before. And presence gets you the best possible VR experience. So this talk is about those biggest hurdles that we faced in hardware and how we achieved and solved those problems. The reason we're all here today is to talk about these 4 ideas and to explain how if we do our job in hardware really, really, really well, the hardware actually disappears.
So one of the other challenges, which I mentioned before, is building a team. How do we build a team that works with a new process that's optimized for VR? In doing this, we learned that everybody has to step out of their areas of expertise. Industrial designers often do the work of mechanical engineers. Mechanical engineers can sometimes do the work of optical engineers. And so we don't actually have any handoffs, and the boundaries of each person's knowledge base ends up growing and expanding into each other's. We also learned that it's a long hardware cycle. We have to build things, and it takes a long time to build and get that feedback cycle. But we also learned that we can't just design things without building prototypes, because you have to use those prototypes to reinform the design. And we can't just start scaling without building those prototypes. So we're working on all of these 3 pillars simultaneously. And we don't design and optimize for any singular component. So I go to vacation in Hawaii sometimes, and I really like to snorkel. So you can imagine if I bought goggles that had the best lenses, the most clear, the most scratch-resistant lenses, but they didn't seal properly around my face and water got in, that would be a pretty terrible experience. And so similarly to that, we can't design for just the best displays or the best lenses or the best audio. We have to optimize for the entire experience. And we've had to do this out in the open. You guys, we've been very open about our hardware development process. You guys have seen the prototypes and the dev kits that we've made. And it takes time. It takes time to make those. So, there you go. Thanks.
So specs are important. We want to get the best possible specs that we can, but we don't just want to do that. We're going to get comfort right. We're going to get fit right. You're going to make this feel comfortable too. We learned a couple things. The most important thing in terms of your comfort is getting optics right and getting the fit on your head right. The fit on your head includes things like ergonomics and also the way the weight's distributed. So the first area we're going to talk about here is optics and focus. You have 2 eyes, we have 2 screens. Getting the right depth perception and focus is really important to get the maximum comfort for each person. Now, ergonomics is really crucial. When we're talking about ergonomics, we want to fit everyone from the 5th percentile female all the way up to the 95th percentile male with one design. This is really, really tough. And if we get this wrong, it won't be comfortable for everybody. The Rift really needs to fit you, all your customers, the whole community between those ranges that I'm talking about. I'm going to introduce a concept called Ipd. Ipd just means the distance between your 2 eyes. It stands for interpupillary distance. Everybody's is different, and you need to make sure that the way the optics are set up in a headset match someone's Ipd for comfort. If you've ever used binoculars, you know that you have to adjust the binoculars to fit your face. or you can't see out of them. And so what we're doing is doing the same thing. We're adjusting the IPD distance to fit you. Now, the Crescent Bay prototype didn't do this. This is a really important feature on the Oculus Rift headset. Our problem as engineers is to get this a really smooth, easy adjustment, and also not to add too much weight or complexity. I'm going to show you the very first prototype we ever made of the IPD adjustment. There it is. Very crude, but it showed us lots of things that we needed to see. And so as product design engineers, we're constantly prototyping. We're making things all the time, really, really quickly, sometimes once a day, once every 2 days, using 3D printing and all the prototyping methods that we can even think of. And we're not just refining the design, because as Stephanie talked about, the way that we're working is everything's coming up at the same time. So what we're having to do is make a design the way that CAD is right now, the way that architecture is right now, and then somebody else is taking up this space, and another feature is taking up this space. And we have to do a redesign and a redesign to get this to work right. That's what working in parallel is like. Even though it ends up making a better product and saving time, it's actually really hard. Every feature is fighting for space. This is the design we ended up with. It's a gear train. It maintains optical alignment, and it gives you that full range to fit all those people I was talking about under incredible space and weight constraints.
So what's the point? What's the point of all of this complexity? This really crazy cool mechanism that you see up here. And the goal is to create better stereoscopic view, to create better depth perception and better 3D. It's a highly cross-functional effort. As Caitlin had mentioned, product designers have to work very closely with the optical engineers to mount the lenses to the display. But then now that we get something that moves, how do we communicate that to software? How do we get that translated into SDK language so that we know exactly what image to render? And so therefore, it requires a lot of collaboration between optics, product design, electrical engineering, and firmware, which is that link between the product design and optical side to the SDK. And again, all of this complexity so that we can get better 3D and create better experiences. So you might ask, well, what if we didn't have it? I'll take you back to that tower example. If the IPD wasn't quite right and you didn't get the perfect depth perception, you wouldn't feel like you were standing on top of a skyscraper. It would almost look probably two-dimensional, or it wouldn't be the right depth perception, and so you wouldn't get that same rush of adrenaline that you would have otherwise gotten. And so again, we go through a lot of complexity and jump through a lot of hoops and hardware to better serve the software and to get a better immersive experience.
Thanks. The mechanism's only part of the issue. The mechanism's coming from the inside. It's the mechanical part. And it needs to work really well. But we also have a human on the other side. We need some way to connect the lenses to the rest of the device, even if those lenses are out here or in here on the range of movement. This is a really, really hard problem. It had to feel good over the whole adjustment. This is our solution. This is the fabric that goes on the inside of the device that connects the lenses to the rest of the device. And it was incredibly tough to figure out. Why is that? You can imagine, we're working with fabric. We're working with people who are used to making clothing. And we're integrating those things into people who are used to working in high technology. And we're going to talk a little bit about why this is so hard in a minute. The hardest work, even though we figured this out, we figured out the IPD mechanism, we have two really good ideas, we haven't even gotten to the hardest part yet. The hardest part is when we connect the two on the inside. This is when the real work begins for product design engineering. We're merging a fabric product with an IPD mechanism. Two separate products from two separate industries coming together. And in this case, is a really good example of how we work, because industrial design actually came across and did engineering work here. An industrial designer figured out how to design this part. In fact, this same industrial designer went into the supply chain and made sure we could source the right fabric. And when we found we couldn't quite get the fabric right, we made a custom fabric. This is a really good example of how to work in VR and how to get this right. It's new, nobody's ever done it before, so it requires everybody to pitch in and help out. In other areas of the design, somebody came over from the engineering side and did work that would be traditionally industrial design work. Fabric is so tough to prototype, which is why we're so lucky we got a helping hand here. About a year and a half ago, the core Oculus team, the original folks, before Stephanie and I joined, decided they wanted to maximize the comfort of the device. And one of the things they tried was to wrap the DK2, our second developer kit, in fabric. Put it up to a sensor, and it actually worked, sorta. And they were like, man, if we could get this to work, this would be amazing. At first pass, we proved it might be possible. Why did we do that? For comfort. When you think about it, you don't wear pieces of plastic in plates. You don't wear hard metal parts. You wear fabric for a reason. It's comfortable, it's compliant, it feels good on your body. And we thought about this as the same thing for the Rift. Ever since we first saw that original prototype, we knew we wanted this. But it was really, really, really hard work to keep this in. We all had to be completely committed. And so the second area I'm going to talk about today is fabric. Imagine you had a beach ball and you were going to give it as a gift, and you had to wrap this beach ball in 2D flat paper, but I told you I didn't want you to have any wrinkles in it. Imagine how hard that would be. That's what we're doing on the Rift. That's one of the problems that we're solving, and this is all in service to better VR. We had to solve engineering problems about fabric, like the force you got when you stretched it. You can imagine talking to a fabric vendor trying to get them to tell you what kind of force you'd get when you stretched the fabric. It was something that we actually had to go out and find out ourselves. We also had to figure out things like infrared light transmissivity. So you can imagine what kind of problems we were hitting up against. This was not an easy marriage between industries. But what we were setting out to do wasn't easy. And we solved a bunch of really interesting problems to do what was best for your VR experience. It's almost without precedent to take 2D fabric and integrate it with high tech. 2D shapes integrated into 3D. And it was a great connection point for us between hardware, industrial design, and our supply chain. We also had to figure out materials. How do we solve this? A mix of iteration, prototyping, and materials. Many of you might have heard the term constellation tracking. Can I get a show of hands? Who's heard of constellation tracking? Great, okay, informed audience. For the folks that don't know, constellation tracking just works where you have LEDs emitting infrared light, and based on how they do that, we use a sensor to pick up which direction you're looking. That's all it is. But it gets a little more complicated when you're trying to do this through fabric. Fabric's got to be, you've got to be able to see the light through the fabric. This is tough. We also learned that tiny little details around the LEDs, like refractions or surface finishes, changing one of those things has huge implications on tracking. And we want to get the head tracking as good as it can possibly be. So this is a picture of light going through fabric. And if you think about it, the fabric acts as a diffuser, and most of the light's going through the gaps. So how far you stretch the fabric means that the number of gaps are changing. This all affects how well you can track. Also, the tiny little diameter of each individual fiber matters a lot as well. We had to solve all these problems, bringing the Rift to you. We used all the prototyping methods we could think of to figure out this problem. You'll notice fabric is everywhere on the Rift. It feels better. It's going to give people better immersion. We got the whole team to buy in on this feature. It was really important for us to make your experience better. It puts the content front and center.
So as Caitlin had mentioned, there are a million reasons to have quit on fabric, but we didn't. And instead, we went on an international scavenger hunt for fabrics, looking for fabrics that did just what we needed to, that had the right IR transmissivity properties, that had the right stretch, that felt good. It's the same as if you're trying to make your custom suit or a custom sweater. You have to have the right pattern, but it also has to feel right. You don't want an itchy wool sweater because you would never want to wear it. So we went around the globe within the US, Japan, Austria, looking for these fabrics. And as Caitlin had mentioned, we didn't find these in many cases, and we actually had to go off and custom develop some. And this is sometimes an example of how the industrial designers went into other industries and other disciplines to help invent the right fabrics that we needed. So now that we have the fabrics identified, we have to figure out how to wrap it and get it to Asia, where we were making the plastics, and we had to get it wrapped around the plastics. So you can imagine the marriage of textile industry with high-tech plastics is not an easy one, and it was a really complex coordination and orchestration of a supply chain all around the globe. We flew a lot of miles trying to get the right fabrics to the plastics and figuring out how to integrate it all. And again, it's a cross-section of two industries with very little cross-section, and we had to get them to talk in the same language. So we had to figure out how to wrap the headset with fabric. We figured out how to do this, but it took an hour. It took an hour to wrap the very first ones. And as you can imagine, that's a very tedious and painstaking process. And taking an hour to do anything really isn't very scalable, nor is it very repeatable. So back to the spirit of having to do things in parallel, we had to design and figure out the engineering behind getting the fabric around this plastic. But we also had to do the engineering to figure out, how do we automate this process? How do we do something that's inherently very difficult to do by hand and make a machine do it, and make a machine do it very quickly? And we knew we had to do this to get repeatability. We want each unit to look very consistent. We have to do it to get the volumes that we need, otherwise this would be like a bespoke suit, which there's not a lot of access to for many people. And we also have to do this to get the cost and volume targets that we needed, so we could try to get VR out as quickly as possible to as many people as possible. So again, we did all these things in parallel: materials investigations, design, automation, all at the same time, so that we could get VR out as quickly as possible and to create the best possible product.
I don't think anybody else is looking at these problems quite the way that we are. I expect some of you have looked at several of these devices, but it's been really, really important for us to make sure that the Rift is beautiful and elegant, as well as working great and comfortable. We took into account all of these things and many more to make sure that we hit that target. I kind of liken this to writing those 2 perfect lines of code instead of the hundreds that could do the same thing. The third area we're going to talk about today is straps. You may think straps aren't that important compared to the front of the headset, but they actually are. They're really important. They support the headset. If you do them right, you can get the same weight feel like much less weight. You could make the headset feel much lighter. Has a huge impact on comfort. Our solution is to combine materials of different types into one strap. We have sections that are compliant and sections that work in different ways to get the straps to fit all the people we were talking about. This is a really tough problem. Head sizes vary quite a lot, so solving this was really tough. If you've tried this device, you know the first thing you do is adjust the Velcro on the top and the sides. You should only have to do this one time. That's the great thing about this design. Once you've gotten it to fit you, we have an automatic adjustment that lets you take it on and off. That's a huge deal for comfort. That's automatic. We've got mechanisms on the left and the right sides with a little bit of spring force. You may also know we have 360-degree head tracking so that when you turn around, we can still perceive where you're looking. This was pretty tough. How do we do this? Well, not only did we have to solve those fabric problems that I was talking about, we also had to get intelligence, another constellation of LEDs, on the back of the device. So this strap, not only is it for ergonomics, for comfort, but it's also got a ton of intelligence in it. It's got signals for the infrared LEDs, and it's also got audio signals embedded in it. The back of the straps cradle your occipital bone, so the top strap is taking on much of the weight. This makes it much more comfortable. Imagine we hadn't done that. We hadn't designed it quite the way we did. You'd have to cinch down the perimeter of the straps, and you'd be using the force against your face to hold the headset up. Our design allows you to use much, much less force around the perimeter of your head. The force against your face is smaller. We just use enough force to conform the part that touches your face and to block the light. This is going to allow you to wear this device for longer and to be more comfortable.
So how did this part get made? As Caitlin had described, there's a lot of complexity in this part. And so the team identified that this would be probably one of the most challenging parts, and one of the ones that would take the longest to develop. In building hardware, things take time. It takes time to go from the point where we're pencils down in the computer or on paper to the time that it takes for us to get our very first prototypes back using production processes. It took 8 weeks for the very first prototype of this strap to come back. Can you imagine writing your code and then waiting 8 weeks for it to compile before you actually ran it? And so you can imagine how anxious we were in these 8 painful weeks of waiting to see what our design looked like. And as expected, with any first design, any first time that you build it, it didn't go as perfectly as we had hoped. But this is normal. This is normal for hardware. So we have to modify. We have to modify the part. We have to modify the design. And when we do that, it takes yet another 4 to 6 weeks to get the next round of prototypes back. So it takes time to release the designs, get them back, evaluate them. And we also have to build these designs into the full headset. We can't design this similarly to how I'm sure many of you guys have written apps and games for a phone or a tablet, where you can simply just have that display and the touch screen mounted on a piece of acrylic with the board, which isn't in the same form factor. We couldn't do that with the strap. We actually had to build it into a full unit. This is also the lifeline of the headset. It takes signals from the front of the headset to the back of the headset so that we can get that back of the head constellation tracking. And it also takes audio signals too, to help get that 3D immersive audio experience. So this is a really expensive part to fail. You can imagine we have to make sure as we're building this that the back of the head LEDs work and that the audio quality is good. So how did we do this? We have a very talented automation and test team, and they work very closely with the design engineers to figure out what are the most important parts to test on this device. And they write custom code, build custom fixtures to find ways to validate that at every point along the manufacturing line that we're building this properly to our specs and that it functions. Because it would be disastrous if we got units off the end of the line that didn't turn on or didn't function as we expected. So again, we have to develop both design, manufacturing processes, and testing processes all in parallel. So imagine you're watching a movie on your laptop and you've got your earbuds in, and the left one stops working. It's probably pretty annoying. It's annoying, but you can still watch that movie. You still pretty much know what's going on. It's not mission critical. But imagine you're being chased by that dinosaur and one of the headset stopped working, or the back of the head LED doesn't work. It's mission critical. It's absolutely mission critical for VR that we can get back of the head constellation tracking and audio working properly. Caitlin will give a more detailed example and more colorful one than I just did.
So imagine you're in a game and you're in the middle of the woods at night and you're creeping up on your enemies and you're going to try to take over their location. But a twig snaps right over here and you turn around and you shoot the bad guy. This is possible in 3D audio. This is going to be amazing. And so we had to make this really awesome, really great experience for everybody who uses the device. Getting this right is critical to immersion. Now, the straps that we just talked about form the base for the audio. The audio clips are the fourth part of what we're going to talk about today. We have a really big challenge with these audio clips. We've got to fit all these different heads. We also want you to be able to take them on and off so you can use another audio solution if you want to. The other trouble with these, the other hard part of the challenge is you've got to be able to keep tracking as great and wonderful as it would be otherwise. So you've got to make sure that they're low profile. We also wanted them to be able to flip up when you took the unit on or off and flip back down. If you think about it mechanically, this is a pretty tall order. How do we think about this? First, imagine the ergonomics problem. We've got to fit a lot of different head shapes and sizes. 95th percentile female to 95th percentile male, that's several inches of head diameter. This is a really big deal. We also have really different ear shapes and sizes. So this clip is going to have to go up and down, back and forth, and also in and out. You've got to figure out how to get this clip to work in different positions. We used ergonomic data to tell us what those numbers should be that we should design for. So if you have a small head, versus a larger head, we've got to solve this problem. I don't know if you've ever been on an airplane and had those freebie headphones. They're really annoying and they don't work. Why don't they work? Because they get the force against your ear wrong. And why does that matter? That force plays off the audio quality. This is something we've really got to nail in order to get immersive audio right. You've got to feel like you have both feet fully in VR. The way we solve this problem is to look at dozens and dozens of mechanisms. We are solving this difficult problem for size and shape, for force, for cost, for consistency. We also didn't want it to be too complex. We decided to use a 4-bar linkage. We used a geometric solver in our 3-dimensional computer-aided design system, and we solved for this average force we want over that whole range. So we're solving for the average of a force curve here. And I'm going to get a little bit more technical to show you what kind of work we do to get every single detail right on the Rift. So on the right, you see our design, and on the left, you're seeing force versus angle. And on all those -10 to 15 degrees, which is all the places we think this is going to be able to contact someone's ear, we want an average force. And we actually solved for that force. We hit our target, and we optimized the ergonomics of this feature. Remember, we wanted removable audio clips, so we had to design removable audio clips for people with their own audio. We also finally wanted the strap to look great, whether the clips were on or off.
So as Caitlin had mentioned, our final design hit our target. But as again, with the straps, just as with straps and with audio, we didn't get it right on the first try. So the first time we put this together, we got the parts back. We realized that it was very difficult to assemble. And in making the parts, it required our manufacturing partners to hold incredibly tight tolerances. And sure, while they could do this, it's not scalable. It takes time. It takes a longer time to make things really precise. When things fall out of tolerance, we can't use them, and so the yields go down and costs go up. So we can't do that. It's akin to making a really high-end watch by hand. So in figuring out this data, after having built the very first few audio arms, we had to go back to the drawing board. We had to go back to the drawing board to figure out a design that was most optimal for both the engineering purposes of serving which directions we need the audio to flip and what the force targets were. But we also had to design it for manufacturability and scalability. And so we often learn in going through this exercise that things that look great and work great on CAD and in paper don't often materialize that same exact way in real life. And that's part of the fun in hardware, is that we design what we think is the best solution on paper, but we actually have to go off and build it. We have to build it and get it back and test it to figure out how close did we get to our goal. And again, in going through this redesign exercise, we learned that we can't ever optimize around any single item. We couldn't just optimize around that design. We had to optimize for assemblability, repeatability, cost. And the whole goal of that was to get the right experience for audio. It was to get the best possible product out there. Now behind me, you'll see a picture of many of the members of our incredibly talented hardware team. And here we are at the factory with all smiles on our face, with the very first rift that came off of the production line. Now rewind 24 hours, we weren't actually all smiles during this build. Problems crop up. But we have teams and engineers that are so passionate about what they do and so invested in this new development process of wanting to do everything in parallel and to move as quickly as we could, that they planned perfectly. We planned to have engineers travel with toolkits, custom toolkits, with anything and everything you could possibly imagine, down to screws, screwdrivers, electrical tape, X-Acto knives, surgical blades, anything you could imagine we had in those toolkits. And it's a true testament to the foresight and the talent of their engineering team that we actually had all of those tools and we actually used them at the factory. Because sometimes you have to get creative when the tools don't always exist at the factory. And we also had vendors who were really passionate and actually engineers who were super passionate about wanting to debug those problems themselves. And that's why you see such a large team here who traveled out to the factory to complete this build. We also had test engineers, as I mentioned, where we created custom test fixtures to be on site to make sure that that moment that that first unit hit the test station, it was up and running, and we could actually confirm that this unit functioned properly. And how smoothly this build went, how close we were able to being, we set a date out for ourselves for being able to put a first unit together, and we hit that date pretty much on the nose. And in normal consumer electronics, going to a first build, it doesn't always happen this way. It's usually delayed. So again, it's how we do things all in parallel, and we were actually able to complete our first build on time.
You guys saw that exploded view of all those different parts that we're putting together. So you can imagine what a big deal it was when we were able to put those together. It was a career first for me to try to put something that complicated together in the factory on the very first try. The first unit we tried to put together went together the way we expected. I really think it was a testament to the product management and project management, as well as the engineering of the group. In my opinion, at this build, we actually outperformed some of the best hardware companies out there, much bigger and older than we are. And I attribute that to the way that we built our team around virtual reality, the way we didn't have serialized handoffs. This allowed us to be really nimble, but it also fostered trust between the teams, and that integration allowed us to get where we needed to go.
So completing this build and getting that very first unit off the line is an example of how we run the program in parallel, how we do things to try to save as much time as we can, and how we try to plan ahead. Though in hardware, we do run up against the limits of time and space. If we could get the parts made faster with production processes, we would. If we could fly around the globe faster, believe us, we would be on those planes. But it takes time. It takes time to get mechanical parts made, electrical parts, and it takes time to fly around the globe. Zuck often says that coders have special powers and superpowers, and that's true. If you think about it, you could write code, compile it, and almost run it instantaneously. But we can't do that with hardware. But I want to assure you that our hardware teams are pouring our hearts and souls into this product to get it just right, to get every detail just right for the experience and for manufacturability, so we can get this out to as many people as possible, to get your content on these devices to serve the audiences that you want. And so again, it's definitely worth the wait because we're pouring our hearts and souls into it just to get every last detail right.
Why are we doing all this work? Why are we doing all this? Sometimes I ask myself. No, people really want to be on that ledge. They really want to be feeling that feeling. That's why. We can't give them that immersion without all this work. It's totally worth it. It takes all that work to get you, the people who use your software, who look at the content, totally immersed. It takes all this work to do that right. This is also new. Nobody else has solved these problems before. That's what makes it so exciting, but sometimes that's what makes it so tough as well. We want the Rift to just work. That's why we got development kits and prototypes to you. We heard what you thought was good, what needed to be changed. We took all that information and poured it into the Oculus Rift. This is worth the wait because the content's going to work better and the audience is going to receive it better. I may be the most critical person at the company about how the headset feels and fits as the leader of the product design and engineering team, except for maybe our CEO, Brendan. This device fell away from me, and I connected to this cute little hedgehog when I tried the Henry demo. That was incredible to me because I was just going in to check this demo out, little animated hedgehog, and I sat down in his room, and I remember seeing his first little friend, a balloon animal, and he gave his friend a hug and popped him, and all his other little friends ran away. And I was really, really surprised. I felt something. I felt bad for Henry. And I never would have felt that if it had just been in 2 dimensions on a screen somewhere. After all the work we put in, the headset disappeared for me during that demo. And it hit me. If you can make people feel like that with this product, with the Rift, you can do anything with it. All this work that we've done is worth it. Now, the Rift is coming out early next year, and we've really made it for you. When you're in VR, you can do anything. You can be anybody, but you've got to have that content. And we can't wait to see what you do with the Oculus Rift. Thank you. Yeah. Go ahead. Good job. You guys want to do a Q&A? Yeah? Okay.
If anybody has any questions, just come right down here and you can talk into the microphone.
Nice.
Hello,
Hey.
my name is Ben Lang from Road to VR, and I was just curious to know, is there a difference between the CV1 headsets that we're seeing here at Connect compared to what we saw at E3? I noticed that on the E3 ones, the Ipd adjustment didn't seem to be active at the time, and as far as I can tell now, they appear to be.
Yeah, that's a good example of something that's different. Every time you make something, you get it a little bit better. I kind of described how complicated the Ipd adjustment was. So we needed one more round to get it right. But remember, E3, I'm not sure it's clear, but we're killing ourselves to get these things out. And we're making them late into the night. So Ipd wasn't something we could quite get ready for E3, but it is on the current units that you're looking at.
Yeah.
Hi, I'm Fan from Wondergate. So I have 2 questions regarding the Ipd adjustment. The first one is a simple one, like have you measured how accurate the user will adjust their Ipd in terms of millimeters?
We do know the data that tells us how accurate you need to be. Yeah, we figured that out and we made sure that the mechanism can supply that granularity of measurement.
Okay, but you cannot tell us how accurate it is.
You can come talk to me after if you want.
The other question is regarding, like you mentioned a lot about like making mechanically adjust Ipd, essentially adding moving part into the product is so hard, but still you decided to move the display and lens to adjust Ipd. What's the problem? I'm pretty sure you guys try to do it without moving part. What's the problem you are facing? Why not use do it in like optical way?
If you can figure out how to do that, you should definitely let us know.
We want you to come work for us.
Yeah, exactly. It's comfort. It's really, we weren't able to find a way to get it to be comfortable over time unless we matched the Ipd. I don't know if you have anything to add to that one, but.
I think if I understand your question right, you're wondering how do you basically move the lenses and displays without actually moving them to adjust for your Ipd?
Yes, because I know like HoloLens also adjusts Ipd, but it does not have any moving part. I just
Right.
wondering why you don't.
Yeah, so our displays and our lenses are fixed, and so we actually have a physical OLED display, and so that can't actually adjust, right? On the HoloLens, they have a Pico projector that actually shines the display into your shines the image into your eye, and so therefore they can change how they do that. Yeah.
Hi there, and apologize if I missed this, but could you speak to the microphones at all? Was there any special challenges or special tweaks that you guys did to that to make it work really well with VR?
The microphones?
Yeah.
We didn't have any particular challenges with it. It was making sure that it was located in the right space on the headset to actually pick up your voice.
Okay. And is it mono or stereo or?
The mic, I think there's just one, actually. I have to ask the electrical engineers, but I'm pretty sure there's only one mic on it.
If you know, you can shout it out. Yeah.
Cool.
Nobody?
There's one, that's right, there's one.
One, in general, when we're looking at mics, what we've got to do is make sure they're located in a way they pick up the sound, but also that there's no obstructions, right? So you got to make sure that you get the adhesive right, that you get the clearances right. And that's something that we have actually been working on as well, to make sure we nail that.
That's one of the
feature.
challenges with fabric too, is that you want to make sure that it's not, the strands aren't actually going to be occluding the mic hole, and that when you're applying that fabric around it, that you're not getting glue in the mic hole or anything that's going to obstruct its ability to pick up your voice. Yeah.
My name's Gerald. I just had a quick question because you guys said you're using fabric, and generally fabric is used on clothing to keep heat in. So how did you guys deal with that challenge of making sure that the components inside the headset could still, release all of their heat and make sure that they didn't overheat? Was that focused on making material that allowed for that, or did you actually design something else for that?
It's a great question. So that inner fabric breathes.
Yeah.
So the fabric up against your face here actually breathes. It's permeable. And that makes it much more comfortable because it doesn't trap. If you could imagine you had a fabric that was backed with some hard substance, it wouldn't be able to breathe up against your face. But the one I showed you could see the light coming through it. It was actually stretchy fabric. So that's part of why we use that fabric there.
Hi, my name is Bart, and I wear prescription glasses, and I don't want to wear contact lenses. So when you talked about binoculars, the good thing about binoculars, of course, is you can adjust focus so you can get clear vision even without your glasses on. Is this something you're looking into for future versions, to do that technically, or is it just going to be like this, or change some lenses?
Good question. This is a tough question. We want to make sure that everybody can use it. I have glasses, and the CV1 works for me right now, the way that we've designed it. We just want to make sure that you get the right clearance. Was that your question? I might have misunderstood.
Exactly.
Okay.
And when I put on CV1, I got large eyeballs here. It gets a little bit pressed out.
Yes.
And when I take them off, it's really the great experience in terms of presence. I don't feel the headset, but it's not that crisp as I want it to be. So it's a little bit of trade-off for me right now.
It's a really good question. It's something that we're working on. I think the trick is that we've got to optimize for all kinds of different things. If you think of field of view, the closer your eyeballs are to the screens, the more field of view that you have. So what we're trying to do is optimize for field of view for everybody, both glasses wearers and non-glasses wearers. And with glasses, you're a little bit further from the screen, so you're not going to have as good a field of view. The reason that we're trying to get the device, and the reason that you're feeling what you're feeling, is we're trying to get your field of view maximized.
Exactly. But there's not going to be some sort of maybe, the lenses, are they still interchangeable?
The lenses are not interchangeable.
Okay.
Yeah.
But so I think you saw some slides where there's that foam facial interface part.
Yeah.
And so as an investigation, we are looking at alternate ones to better serve folks who are wearing glasses or who have different size and shapes of faces.
I don't think we're able to commit to the design that we're looking at, but we are looking at a way to enhance comfort for glasses wearers right now for this design.
Okay, great.
Hi, I'm Jeffrey Martin from Sphericam. First, I'd like to congratulate you on what is obviously an extremely complex device. But it looks to me more like the iPhone 5, not the iPhone 1. And I'm wondering how you're balancing the, you have a lot of developers who want to release games to the public. You have other headsets which might come from China and be significantly cheaper than yours. And how do you balance jump-starting the ecosystem with releasing something that you want to be as perfect as possible?
I think we can already get the ecosystem jump-started with what's out there, like the DK2s and the Crescent Bays. But yeah, you are right that our headset is very beautiful, and again, it's how do we better serve the content. Because it's one thing to have content out there and have a lot of it, but if there's no good way to actually consume it, it's not really, I don't know, to me it's not really quite worth it. So again, yeah, we're trying to get more crescent bays out there, and there's a lot of DK2s already out there, and the whole point of those was to actually jumpstart that ecosystem. Yeah.
Thanks.
I'd like to return to the issues IPD. Is part of your design or future design one that could accommodate asymmetry in the interpupillary distance, meaning the distance from the center of the nose to one side is different, significantly different than the center of the nose to the other?
Yeah, it's a really good question. I hadn't thought about it till you just said it, but theoretically, there's definitely a way to think about that. So let us think about that a little bit. I hadn't thought about that, but I guess you're right. Not everybody would have a perfect distance from their center of their head to their eye. So theoretically, yes, but we don't have it in this product right now.
Thank you.
Yeah. Just to finish on that, there's gearing inside, and so everything is linked right now.
It is.
Yeah.
Hi, how's it going? Craig Douglas from Context CI. I was just curious about the runtime on the production, like how long you're getting from when you start the production and when you're seeing it come out. And you touched on the automating of putting the fabric around being pretty difficult within the actual sphere of making the hardware. Outside of that, which was kind of the hardest process to automate since you custom each design?
I would say one of the challenges was, so you see the constellation of LEDs, and they live on a flexible printed circuit board, and we have to align those in assembly onto the housings and then the front plate. And doing that is actually the very first builds that we did was very manual, and you have to sit there and try to press out each one down, and there are certain, because refraction is so important, there are certain ways that we create that stack up, and so that's probably one of the trickiest, or one of the more tricky automation processes is how do we get a machine that takes these flexes, plops them down exactly where they need to be.
And the straps were really tough.
Straps too.
We're actually molding hard and soft parts together, that whole strap piece, in the same tool. And that's kind of insane. Yeah. Like, some of the injection molding people look at us and they're like, you're crazy that you want to do this. We think it looks awesome. There's no seams in those places that we're putting it all together. But that was actually really tough. It took a long time, and we actually had to start much earlier, as Stephanie mentioned in the talk.
So then with the system you're going with now, like what, from the time you hit start on production till like that first one's coming off, how long is that run taking you guys?
So I probably can't comment on that because that's part of our factory ramping simulations, but typically probably on the order of around 100 per hour, around there, okay. Ballpark. Yeah.
Pretty impressive. Awesome. Thank you.
In your presentation, you didn't talk too much about the lenses themselves. Can you talk a little bit about how they're manufactured and the process or evolution from kind of the DK1 all the way through?
The lenses are molded Fresnel lenses. Unfortunately, our optical engineer is not here to give you the details.
What we did, though, I can talk about how we changed the perimeter of them.
Yeah, we can talk about
If you think about it, when we're talking about that small IPD, if you got your eyes really close together, your nose is going to, am I super loud? Oh. Your nose is going to kind of get in the way. So we actually had to change the profile of the lenses to cut away this part and actually this part as well, so they could get as close as possible. So we did a lot of really complex design processes on those lenses to get them to allow that full range of IPD mechanism.
Yeah, so similarly to like plastic parts, they are made in an injection tool. It's just a very, very high precision injection tool to create those lenses. Yep.
I really like the blown apart picture. I was curious, how many parts are we looking at there? Like how many individual pieces?
140.
Jared, do you remember?
Do you know, Jared? There's 63 injection molded parts.
There's like 90 complete custom small mechanical parts. That does not include any of the components.
Yeah.
Oh, so more than that. So that's 150 plus 10,
200s.
15.
It's probably in the order of low hundreds, like probably
Without screws.
probably about 200 to 300 all.
It's a lot.
Go in there. It's
Wow.
a lot of parts.
Yeah.
It's a lot of parts.
Thanks.
Yeah. Thank you. All right. Thanks so much for coming,
Yeah,
guys.
thank you.
Really appreciate it.